Tonight, we are going to travel back as far as it is possible to go. We are going to rewind the clock of the cosmos, past the age of humans, past the age of dinosaurs, past the formation of the Earth and the Sun. We are going to the very beginning. But before we drift back to the birth of time itself, I invite you to subscribe to this channel and leave a comment below if these journeys help you find rest. Your support allows us to continue exploring the universe together. Now, let your shoulders drop. Let your breath slow. We are going to witness the first second of the universe. To understand the beginning, we must first imagine the nothingness. But this is difficult, because the nothing that came before the universe was not empty space. It was not a dark room waiting to be filled. There was no room. There was no dark. There was no time to wait in. There was only a singularity, a point of infinite density and infinite heat, infinitely small. It contained everything that ever was and everything that ever will be. The water in the oceans, the iron in your blood, the light of the stars, all of it was crushed together into a speck smaller than an atom. It was a seed, suspended in a void that did not exist. And then, for reasons we still do not fully understand, the seed opened. It did not explode into space, because there was no space. It expanded, and in doing so, it created space. It created the stage as it began the performance. This was the Big Bang. The first moment is known as the Planck Epoch. It is the sliver of time from 0 to 10 to the power of minus 43 seconds. It is a unit of time so small that it defies human comprehension. In this moment, the laws of physics as we know them did not exist. Gravity, electromagnetism, and the nuclear forces were all fused into one single unified superforce. Reality was a perfect, symmetrical hot unity. Then the symmetry broke. Gravity separated from the other forces, and this separation triggered an event of unimaginable violence and beauty: inflation. Inflation was the breath that blew up the balloon. In a fraction of a second, a trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor of 10 to the power of 26. It went from the size of a subatomic particle to the size of a grapefruit, and then to the size of a galaxy in less time than it takes for light to cross a single atom. This expansion was faster than the speed of light. This does not break the laws of physics, because space itself can expand at any speed it chooses. It carried the energy of the singularity outward, stretching it smooth. It took the tiny quantum jitters of the beginning and stretched them into the seeds of future galaxies. If you were there would be no light to see. The universe was not transparent. It was a dense, opaque fluid of pure energy. It was a quark-gluon plasma. Imagine a soup. But this is not a soup made of water and vegetables. It is a soup made of the fundamental building blocks of matter, heated to trillions of degrees. Quarks are the tiny particles that make up protons and neutrons. Gluons are the sticky particles that hold them together. In today's cold universe, quarks are never found alone. They are always locked inside atoms, but in that first second, it was too hot for them to bond. They swam freely in a sea of fire. They collided, interacted, and annihilated in a chaotic, fluid dance. It was the most energetic state matter has ever achieved. As the inflation stopped, the energy of the expansion was dumped back into the plasma. The universe was now a hot, seething fireball, expanding and cooling rapidly. This is the reheating phase. And in this fire, a war was waging, the war between matter and antimatter. For every particle of matter created from the energy, a twin particle of antimatter was also created. A quark and an antiquark, an electron and a positron. When they met, they annihilated each other, turning back into pure light. Billions of times a second, particles materialized from the energy, lived for a microsecond, found their twin, and vanished in a flash of gamma radiation. It was a cycle of creation and destruction that should have left nothing behind. The universe should have ended up as a bath of pure light, with no matter left to build stars or planets. But something remarkable happened. A tiny imperfection, a symmetry violation. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. When the great annihilation finished, when the battlefield cleared, that one extra particle survived. That tiny fraction of a percent is what makes up everything we see today. Every galaxy, every sun, every grain of sand is made of the leftovers, the survivors of the first second. We are the lucky few. As the first second ticked on, the universe continued to expand. And as any gas does when it expands, it cooled. The temperature dropped from trillions of degrees to mere billions. This cooling is the key to creation. It allowed the forces of nature to freeze out one by one. First gravity, then the strong nuclear force, then the weak nuclear force, and electromagnetism separated. They became distinct. The rules of the game were being written in real time. At 1 microsecond old, the universe had cooled enough for the strong nuclear force to take hold. The free-swimming quarks began to slow down. They reached out to one another. The gluons, the carriers of the strong force, snapped them together like magnetic wandering stars. 3 quarks bound together formed a proton. Another 3 formed a neutron. For the first time, the building blocks of the atomic nucleus existed. The soup was thickening. It was no longer a plasma of quarks. It was a plasma of heavy particles, hadrons, but it was still too hot for them to stick together permanently. Protons smashed into neutrons and bounced off. They were moving too fast. The universe was a blindingly bright, incredibly dense fog of particles crashing into each other at nearly the speed of light. And it was loud. We think of space as silent, but the early universe was filled with sound. Pressure waves rippled through the plasma, sound waves driven by gravity and radiation. These were the baryon acoustic oscillations. They were the deep, resonant hum of the cosmos ringing like a bell. These sound waves compressed the gas in some places and thinned it in others. They created the blueprint for where the galaxies would eventually grow. The structure of the modern universe, the vast cosmic web of galaxy clusters, is a fossil record of the sounds that played during the first few minutes of time. As the seconds turned into minutes, the temperature dropped further. It reached a critical point, 1 billion degrees Kelvin. This was cool enough for the next great assembly. A proton and a neutron collided, but instead of bouncing off, they stuck. They formed a nucleus of deuterium, heavy hydrogen. Then another proton slammed into the deuterium, and another. They fused. They formed helium. This was the era of Big Bang nucleosynthesis. The entire universe was acting like the core of a star. It was a fusion reactor spanning all of space. In these few frantic minutes, the universe forged the elements. It made vast amounts of hydrogen, about 75% of all matter. it made helium about 25%, and it made tiny traces of lithium and beryllium. And then it stopped. The universe expanded too much. The density dropped. The protons and neutrons were too far apart to find each other. The fusion furnace shut down. The chemical composition of the cosmos was set. For millions of years to come, this ratio, hydrogen and helium, would remain unchanged. It was the raw material. The clay was mixed, but it had not yet been shaped. Rate 100%, pitch 1%, but there was still a problem. The universe was still opaque. Light existed. Photons were everywhere, born from the annihilation of matter and antimatter, but they could not travel. The universe was filled with free electrons, tiny, negatively charged particles that were still moving too fast to be caught by the atomic nuclei. Electrons are like a fog for light. When a photon tries to move, it hits an electron and scatters. It bounces. It ricochets. Imagine trying to shine a flashlight through a glass of milk. The light is there, but it cannot form an image. It is just a glowing white haze. This was the state of the universe for the next 380,000 years. It was a glowing, hot, dense fog. There was no night. There was no day. There was only the blinding white everywhere. Gravity continued its slow work in the background. It pulled on the dark matter. It pulled on the clouds of hydrogen and helium. It tried to build structures, but the radiation pressure, the intense heat of the trapped light, pushed back. It was a stalemate. The universe had to cool down. It had to expand. It had to stretch. And slowly, over thousands of millennia, it did. The orange glow of the plasma faded to red. The temperature dropped to 3,000 degrees Kelvin, about the temperature of the surface of a red dwarf star. And then, the moment of clarity arrived. The electrons slowed down just enough. They lost their frantic kinetic energy. As they drifted near the positively charged nuclei of hydrogen and helium, the electromagnetic force reached out and grabbed them. Click. The electron was captured into orbit around the proton. The electric charges canceled each other out. The atom became neutral. This event is called recombination. It changed everything. Neutral atoms do not scatter light in the same way that free electrons do. They are transparent. Suddenly, the fog vanished. The cage was opened. The photons, which had been trapped in a pinball game for 380,000 years, were suddenly free. They streamed outward in every direction, traveling in straight lines for the first time. The universe burst into light. If you had been there to see it, it would have been like being inside the sun, and then suddenly, the sun vanishing, leaving only the clear sky. This light is still traveling today. It has been stretched by the expansion of the universe. It started as visible orange light, but over 13 billion years it has stretched into the infrared and then into microwaves. We call it the cosmic microwave background, CMB. It is the oldest light in the universe. It is a baby picture of the cosmos, taken just after it was born. When we point our radio telescopes at the sky, we see it everywhere. It is a uniform glow coming from every direction. It is the afterglow of the Big Bang. It is almost perfectly smooth, but not quite. There are tiny fluctuations in the temperature, variations of 1 part in 100,000. These tiny spots, some slightly warmer, some slightly cooler, are the seeds we spoke of earlier. The cooler spots are denser. They have slightly more gravity. These are the places where the first stars will eventually form. But for now, after the flash of recombination, the universe did something unexpected. It went dark. The background glow faded into the infrared, invisible to human eyes. There were no stars yet to light the void. The hydrogen gas was cold and neutral. We entered the cosmic dark ages. Imagine a darkness deeper than any night we know, a silence that spanned hundreds of millions of light years. In this dark, gravity was working. It was the only active force. In the silence, the gas was pooling. The dark matter was building scaffolds. The universe was taking a deep breath before the lights turned on. The first second had created the stage, the actors, and the script. It had forged the matter and the laws of physics. Now, the play could begin. The chaos of the inflation, the heat of the plasma, the violence of the annihilation, all of it settled into a calm, drifting expansion. The energy had become matter. The matter had become atoms. The atoms were waiting. Waiting for the pressure to build. Waiting for the density to cross a critical threshold, waiting for the first spark of fusion to ignite the long night. This journey from the singularity to the dark ages is the story of order emerging from chaos. It is the story of cooling. Entropy began its march. The arrow of time was fired. The conditions for life were set, though life itself was still billions of years in the future. As we drift in this ancient darkness, floating in the clouds of pristine hydrogen, we can feel the potential. We can sense the gravity pulling, gathering, coalescing. We are standing on the edge of the stelliferous era, the age of stars. In the next chapter, we will watch the end of the dark ages. We will see the first lights turn on. We will witness the birth of the first stars, the population 3 stars, monsters of pure hydrogen, hundreds of times massive than our sun, burning with a violet fury that reionized the universe. We will see how they lived fast and died young, exploding as supernovae to seed the void with the first heavy elements, the carbon, oxygen, and iron that would one day make up our bodies. But for now, rest in the quiet of the cooling cosmos. The fire of the beginning has passed. The universe is smooth, silent, and vast. Feel the expansion carrying you gently outward. You are riding the wake of the Big Bang. You are part of the energy that survived. The atoms in your body were there, in that plasma. The electrons in your fingertips were part of that fog. You are as old as the universe itself. The blinding flash of the beginning has faded. The universe has become transparent, releasing the first light to travel freely across the void. But as space expands, that light is stretched. It shifts from the visible orange of a cooling ember into the invisible infrared, and then into the cold silence of microwaves. The universe plunges into shadow. We enter the era known to cosmologists as the cosmic dark ages. Imagine a darkness deeper, wider, and more absolute than any night you have ever known. It is a darkness that spans hundreds of millions of light years. There are no stars to prick the velvet blackness. There are no galaxies to spiral in the deep. There is only the silent, expanding sea of neutral hydrogen and helium, drifting in the cold. To a human eye, this era would appear empty. But it is not empty. It is pregnant with potential. In the silence, a great work is being done. Gravity, the patient architect of reality, is beginning to sculpt the future. It is working in the dark, pulling on the subtle irregularities left behind by the Big Bang. But gravity has a partner in this work, a ghost that we cannot see but whose presence is undeniable: dark matter. While the ordinary gas, the hydrogen and helium, was trapped by the pressure of radiation for thousands of years, the dark matter was free. It did not feel the heat. It did not interact with the light. It answered only to gravity. So, long before the first atom formed, the dark matter had already begun to clump. It formed a vast, invisible scaffolding, a cosmic web of filaments and knots stretching across the void. It dug the wells into which the ordinary matter would eventually fall. Now, in the quiet of the dark ages, the hydrogen gas begins to sense these wells. It feels the pull of the invisible halos. Slowly, inevitably, the gas begins to flow. It streams down the gravitational valleys, gathering in the centers of the dark matter knots. The universe is sorting itself out. As the gas gathers, it becomes denser. And as it becomes denser, it heats up. This creates a problem. Hot gas has pressure. It wants to expand. To form a star, the gas must collapse, but the heat pushes back against the gravity. It is a stalemate. In the modern universe, dust and heavy elements like carbon help gas clouds cool down by radiating heat away. But in this primordial time, there is no carbon. There is no dust. The gas is pristine. It is chemically pure. Because of this, it stays hot. It resists the collapse. This means that to overcome the pressure, you need a lot of gravity. You need a massive amount of gas. The clouds that form the first stars are gigantic, far larger than the clouds that form stars. Today, nature is painting with a broad brush. Finally, the threshold is crossed. In the centers of the most massive dark matter halos, the gravity becomes overwhelming. The gas clouds, weighing thousands of times the mass of our sun, begin to fall inward. They spiral down, spinning faster and faster, heating up as they crush together. Deep in the core of these collapsing giants, the temperature climbs past the critical point. The hydrogen atoms, which have drifted in the cold for 100 million years, are suddenly slammed together with violent force. Quantum tunneling bridges the gap. The strong nuclear force snaps shut. Fusion begins. A spark is lit in the deep dark. A shock wave of energy fights its way to the surface of the cloud. And then, for the first time since the Big Bang, a new light shines. The cosmic dawn has arrived. These first stars, known to science as population 3 stars, are unlike anything we see in the sky today. They are monsters. Because they formed from such massive, warm clouds, they are enormous. They are hundreds, perhaps 1,000 times the mass of our sun. They do not burn with a gentle yellow light. They burn with a terrifying electric intensity. Their surface temperatures are scorching, tens of thousands of degrees. They shine not in the visible spectrum, but in the violent ultraviolet. They are blindingly blue-white, beacons of fury illuminating the pristine void. If you could stand on a planet orbiting one of these giants, though no planets existed yet, the sun would take up half the sky, pouring out a radiation so intense it would strip the atmosphere away in seconds. They are the rock stars of the cosmos, living fast, burning bright, and destined to die young. While our sun will live for 10 billion years, a population 3 star lives for only a few million. They consume their fuel with reckless abandon, desperate to hold up their own crushing weight against gravity. They are engines of pure conversion, turning matter into light at a rate that defies comprehension. But their light does more than just shine. It changes the universe. The ultraviolet photons streaming out from these first stars hit the surrounding gas, the neutral hydrogen fog that has filled space since recombination. These photons are energetic enough to knock the electrons off the hydrogen atoms. They ionize the gas. They undo the work of the early universe. Around each star, a bubble of transparent ionized gas begins to grow. It is like a hole being burned in a fog bank. This is the epoch of rionization. As more and more of these monster stars ignite, the bubbles grow. They merge. The fog of the Dark Ages is slowly burned away, eaten by the light of the first suns. The universe is becoming transparent again, but this time it is filled with structure. But the true legacy of these stars lies not in their light, but in their hearts. Deep in their cores, a frantic alchemy is taking place. The fusion reactor is running hot. Hydrogen fuses into helium. Helium fuses into carbon. Carbon into oxygen, neon, silicon. For the first time, the universe contains something other than the simplest gases. The ingredients for water, for rock, for life, are being forged in the bellies of these primordial titans. They are the first factories of matter. And then the fuel runs out. The collapse begins. But because these stars are so massive, their death is not a gentle fading. It is a cataclysm. Some of them explode as pair instability supernovae. This is a violent, total disruption. The core gets so hot that high-energy gamma rays turn into pairs of electrons and positrons. This drops the pressure suddenly. Gravity wins instantly. The star collapses, triggers a runaway nuclear explosion, and blows itself entirely apart. Nothing is left behind. No black hole, no neutron star, just an expanding cloud of heavy elements. Others are too heavy even for that. They collapse directly. The core implodes, crushing down past the neutron star stage, tearing a hole in the fabric of reality. They form the first black holes. These black holes are the seeds of the future. They are born in the centers of the gas clouds, and they immediately begin to feed. They swallow the gas around them. They merge with other black holes. They grow. They will become the anchors for the first galaxies. They are the supermassive monsters that lurk in the hearts of all modern spiral galaxies, including our own. We owe the structure of our home to these dark remnants of the first dawn. But let us look at the debris field. The gas clouds that were once pristine hydrogen are now polluted. They are enriched with the ash of the dead giants. They contain carbon dust, oxygen molecules, flecks of iron. This change is permanent. The universe has lost its innocence. It can never again form population 3 stars. The dust cools the gas too efficiently, causing it to fragment into smaller pieces. The next generation of stars, population 2, are smaller. They are more stable. They can live longer. They are the bridge between the monsters of the dawn and the gentle suns of today. As gravity continues to pull, these new stars do not form alone. They form in clusters. Hundreds, thousands, then millions of stars are born together, bound by their mutual gravity and the dark matter halo that cradles them. The first proto-galaxies are born. They are messy, chaotic blobs of light. They are not the majestic spirals or giant ellipses we see today. They are clumps of star-forming violence, colliding with each other, merging, growing. It is a time of cosmic construction. The universe is building its cities. The dark matter web is lighting up, tracing the filaments with pearls of starlight. In the centers of these young galaxies, the black holes are feeding. As gas falls into them, it heats up and shines with the brilliance of 1 trillion suns. These are the quasars. They are the lighthouses of the early universe, visible across billions of light years. They blast jets of plasma into the void, stirring the gas regulating the growth of the galaxy. It is a dynamic, turbulent, creative era. The universe is waking up. This process, the end of the Dark Ages and the Rionization, took nearly 1 billion years. It was not a single day of sunrise, but a slow, steady conquest of light over shadow. By the time it was finished, the universe looked different. It was no longer a smooth fog. It was a sponge made of empty voids surrounded by walls of galaxies. The structure of the modern cosmos was set. We are the distant beneficiaries of this time. The carbon in your DNA was not made in the sun. It was made in a star that died before the Earth was born. The iron in the steel of your car was forged in the heart of a supernova that exploded in the deep past. Every atom in your body that is heavier than lithium has a history. It has been inside a star. It has traveled through the explosion. It has drifted in the nebulas of the second generation. We are made of recycled star stuff. The cosmic dark ages are gone, but they are not forgotten. We can still see them. When astronomers use radio telescopes to look at the 21-centimeter line, a specific radio signal emitted by neutral hydrogen, they are looking back to this time. They are mapping the fog. They are seeing the shadows of the first halos before the lights turned on. It is a ghost signal from a time of silence. It reminds us that the universe was not always like this. It has a history. It evolves. It grows up. The transition from the first second to the first billion years is the story of complexity emerging from simplicity. It is the story of gravity organizing chaos. Now, the stage is set for the next act. The universe has galaxies. It has stars. It has heavy elements, but it is still wild. In the next chapter, we will fast forward. We will watch the galaxies mature. We will see the chaotic blobs settle into beautiful, spinning disks. We will see the birth of the Milky Way. We will zoom in on a specific cloud of gas in a quiet spiral arm, a cloud enriched by generations of dead stars, a cloud that is pregnant with a very special potential. We will watch the birth of the solar system. We will see the sun ignite, not as a monster, but as a steady guardian. We will see the dust grains sticking together to form pebbles, then boulders, then worlds. For now, float in the light of the first stars. Feel the intensity of their blue fire. They are the pioneers. They burned so that we could be built. The darkness has receded. The universe is awake. The long night is over. We have seen the first stars ignite, tearing through the fog of the Dark Ages. We have seen them live fast and die young, seeding the universe with heavy elements. But the universe is not just a collection of lonely stars. It is a collection of cities. Now, we must watch these cities rise. We must watch gravity pull the scattered lights together into the magnificent swirling structures we call galaxies. This process begins in chaos. The early universe, 1 billion years after the Big Bang, is a violent place. The first proto-galaxies are not the elegant spirals we know. They are messy, irregular blobs of gas and stars. They are train wrecks in slow motion. Gravity is relentless. The dark matter halos are merging. As they crash into each other, they drag the visible matter, the gas and the stars, along with them. These collisions are the building blocks of structure. Imagine two massive clouds of gas falling toward each other. As they approach, they don't just smash head-on. They swing past each other, caught in a gravitational dance. They spiral inward, and as they spiral, they begin to spin. This is the birth of angular momentum on a galactic scale, the conservation of spin. Just as a figure skater spins faster when she pulls her arms in, the collapsing gas cloud spins faster as it shrinks. This spin has a profound effect on the shape of the galaxy. Gravity wants to pull everything into a sphere, a ball, but the spin fights back. It pushes the material outward at the equator. The result is a compromise, a disk. The messy blob flattens out. It becomes a pancake of stars rotating around a central core. This is how the spiral galaxy is born. It is a balance between the pull of the center and the speed of the spin. But the center is not empty. In the heart of every forming galaxy, a monster is growing, the supermassive black hole. We still do not know exactly how they got there so quickly. Some may have formed from the collapse of the very first population 3 stars. Others may have formed from the direct collapse of massive gas clouds that never became stars at all. However they were born, they are hungry. They sit at the bottom of the gravitational well, where the gas is thickest. They feed. As the gas spirals into the black hole, it heats up to millions of degrees. It shines with the light of 1,000 galaxies. This is a quasar. Quasars are the lighthouses of the infant universe. They are visible across billions of light years. But they are not just passive lights. They are engines. The energy pouring out of a quasar is so intense that it pushes back against the infalling gas. It creates a galactic wind. This wind blows the gas out of the center of the galaxy, starving the black hole and stopping the formation of new stars. This is a crucial feedback loop. The black hole regulates the growth of the galaxy. If the galaxy tries to grow too fast, the black hole wakes up and blows the fuel away. If the galaxy stops growing, the black hole starves and goes to sleep. They are locked in a symbiotic relationship, growing together over billions of years. While the black hole manages the center, the disk is busy making stars. In these early days, the star formation rate is incredibly high. It is a starburst era. The galaxies are factories running at maximum capacity. Gas clouds collapse, ignite, and explode as supernova, all within a few million years. The explosions send shock waves through the disk, triggering the collapse of neighboring clouds. It is a chain reaction of creation. The galaxy glows blue with the light of hot, young stars. But it is also dusty. The supernovae produce vast amounts of soot and dust. This dust blocks the visible light, making the young galaxies look dark and shrouded to our eyes. But if we look in the infrared, using telescopes like the James Webb, the dust glows. We can see the heat of the nursery. We can see the stars being born inside their cocoons. Over time, the collisions become less frequent. The universe is expanding, moving the galaxies further apart. The frantic mergers of the early days slow down. The galaxies have time to settle. The chaotic currents in the disk smooth out. The spiral arms emerge. These arms are not solid structures. They are density waves, ripples of gravity moving through the disk like traffic jams on a highway. As gas clouds move into the spiral arm, they get compressed, they slow down, they form stars. Then the stars move out of the arm and continue their orbit. The spiral arm is a standing wave of star formation, a permanent pattern made of temporary stars. It is beautiful. It is the signature of order emerging from chaos. And among these settling galaxies is our own, the Milky Way. It began as a small clump of dark matter and gas. It grew by swallowing its neighbors. It ate smaller dwarf galaxies, stealing their stars and their gas. We can still see the remnants of these meals today. Streams of stars circling the Milky Way halo are the crumbs of galaxies that were digested billions of years ago. Our galaxy is a cannibal, but it is a benevolent cannibal. It uses the stolen material to build. About 9 billion years after the Big Bang, about 4.5 billion years ago, something happened in a quiet spiral arm of the Milky Way. A cloud of gas and dust, enriched by the deaths of previous generations of stars, began to collapse. Maybe it was nudged by the shockwave of a nearby supernova. Maybe it just got too heavy. It shrank, it spun, it flattened into a disk, and in the center a yellow star ignited. Our sun. It was not a monster star. It was modest, stable. It was a main sequence star designed to burn slowly for billions of years. It was the perfect hearth for a long story. Around the new sun, the leftover dust and gas formed a disk, the protoplanetary disk. In this disk, the dust grains began to stick together. Electrostatic forces pulled them into tiny clumps. Then gravity took over. The clumps became pebbles. The pebbles became boulders. The boulders became planetesimals, mountains floating in space. It was a violent shooting gallery. The planetesimals smashed into each other. Some shattered, others merged. The winners grew larger. They swept up the material in their orbits. Close to the sun, where it was hot, only rock and metal could survive. This formed the inner planets: Mercury, Venus, Earth, Mars. Further out, past the frost line, it was cold enough for water and gases to freeze. Here, the planets could grow huge. They captured massive amounts of hydrogen and helium before the sun blew it away. This formed the gas giants: Jupiter, Saturn, Uranus, Neptune. The Earth, in those early days, was not a blue marble. It was a ball of molten magma. It was hell. It was bombarded by asteroids and comets. One collision, a Mars-sized object named Theia, smashed into the young Earth so hard that it splashed a ring of molten rock into orbit. This ring coalesced to form the Moon. For millions of years, the Earth cooled. A crust formed. Volcanoes erupted, spewing steam and carbon dioxide into the atmosphere. Comets, carrying ice from the outer solar system, rained down. They delivered the water. The steam condensed. It rained for centuries. The basins filled. The first oceans were born. The stage was set. The physics was done. The chemistry was ready. But the universe was still a dangerous place. The young sun was dim, but it was prone to violent flares. The solar system was filled with debris. Life, if it was to start, would have to be tough. It would have to start in the deep, protected places. The story of the universe, from the first second to the formation of the Earth, is a story of cooling. It is a story of energy spreading out, finding new forms. From the quark-gluon plasma to the proton, from the proton to the atom to the star, from the star to the heavy element, from the element to the dust, from the dust to the planet. It is a cascade of complexity. Each step builds on the one before. And now, on this wet, rocky world, a new kind of complexity was about to emerge. A complexity not of nuclear fusion or gravity, but of information, of biology. In the next chapter, we will watch the spark of life. We will not look at how it started. That remains a mystery, but we will look at what it did. We will see how single-celled organisms terraformed the planet. We will see the great oxygenation event, where blue-green algae poisoned the atmosphere with oxygen, killing almost everything but paving the way for us. We will see the slow climb from the ocean to the land. But for now, hover above the young Earth. It is 4 billion years ago. The moon is much closer, huge in the sky. The tides are massive waves rushing across the global ocean. The air is red with methane and carbon dioxide. There is no green. It is a harsh, alien world, but it is home. It is the result of 9 billion years of cosmic evolution. Everything that happened in the first second, the ratio of matter to antimatter, the strength of gravity, the speed of light, conspired to create this rock, this water, this moment. You are the result of that conspiracy. The atoms in your hand were once inside a star that died to make you. The water in your blood was once ice on a comet. Rest in that deep connection. You are not in the universe, you are of it. Drift in the orbit of the young sun. We have watched the universe build itself from a single point of infinite heat into a majestic clockwork of galaxies and stars. We have seen the Earth coalesce from the dust of the solar nebula, a molten ball cooling in the vacuum. Now, we hover above this young world. It is 4 billion years ago. If you looked out the window of a spacecraft at the Archean Earth, you would not recognize it as home. It is an alien planet. The sky is not blue. It is a hazy, toxic orange, rich in methane and carbon dioxide. The oceans are not blue. They are olive green, saturated with dissolved iron. The continents are stark, barren rock, black and gray, with no hint of green. There is no sound but the wind and the waves. It is a silent, waiting world. But deep beneath the surface of those iron-rich seas, something is happening. A threshold is being crossed. The universe is about to perform its greatest trick. It is about to wake up. It is about to transition from dead chemistry to living biology. We do not know exactly where it happened. It might have been in a shallow, sun-warmed tidal pool, where molecules were concentrated by evaporation. Or, more likely, it was in the crushing dark of the deep ocean, along the ridges of hydrothermal vents. These vents act as chemical chimneys. They spew mineral-rich, superheated water from the Earth's crust into the cold ocean. The contrast between the hot, alkaline fluid and the cool, acidic seawater creates a chemical gradient, a natural battery. Energy is flowing. In the microscopic pores of the rock chimneys, complex molecules begin to gather. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the KNOPS elements forged in the stars, begin to link up. They form chains, amino acids, nucleotides, lipids. For millions of years, this chemical soup churns. It is a game of trial and error played by trillions of molecules over eons. And then, one day, a specific arrangement forms. A molecule that can do something new. It can copy itself. This is the moment of a biogenesis, life from non-life. The molecule copies itself, but imperfectly. The errors are mutations. Some copies are better at surviving than others. Evolution begins. Soon, these replicating molecules become trapped inside tiny bubbles of fat, lipids. This is the first cell, the first membrane. It separates self from world. Inside the bubble, the chemistry is protected. Outside, the ocean rages. This first life form, we call it Luca, the last universal common ancestor, is microscopic, simple, and fragile. It eats the chemical soup of the vents. It lives in the dark, but it is alive. It has agency. It wants to persist. Rate 100%, pitch 1%. For 1 billion years, life remains small. It is a slime world. Bacteria and archaea dominate the planet. They cling to rocks. They float in the water. They are anaerobic. They do not need oxygen. In fact, oxygen is a poison to them. But evolution is restless. It is always looking for a better energy source. The chemical soup of the vents is limited, but up above, beyond the surface of the water, there is a virtually infinite source of power: the sun. About 2.5 billion years ago, a specific type of bacteria, cyanobacteria, stumbles upon a new technology. It develops a pigment, chlorophyll. This pigment allows the cell to drink sunlight. It allows it to split water molecules to get electrons. As we explored in the story of light, this process releases a waste product, a gas, oxygen. At first, the oxygen is absorbed by the ocean. It reacts with the dissolved iron. The green oceans turn red as the iron rusts and falls to the sea floor. This rust forms the banded iron formations we mine today. The steel in your car was laid down by bacteria billions of years ago. But eventually, the iron runs out. The ocean cannot hold any more oxygen. The gas bubbles up. It breaks the surface. It enters the atmosphere. This leads to the first global catastrophe, the Great Oxygenation Event. To the anaerobic life that ruled the Earth, oxygen was a toxic sludge. It burned them. It destroyed their cellular machinery. As the oxygen levels rose, it triggered a mass extinction of microbial life. 99% of life on Earth may have died. It was a holocaust caused by the invention of breathing. The catastrophe worsened. The methane in the atmosphere, which had acted as a greenhouse gas keeping the Earth warm, reacted with the oxygen and turned into carbon dioxide and water. The greenhouse blanket was stripped away. The temperature plummeted. The Earth froze. Ice sheets spread from the poles all the way to the equator. The entire planet became a white, frozen ball hurtling through space. This was the snowball Earth, or the Huronian glaciation. For hundreds of millions of years, the Earth was locked in ice. The life that survived huddled near the volcanic vents, or in thin pockets of water beneath the glaciers. It seemed like the experiment of life had failed. The cyanobacteria had been too successful. They had frozen their own world. But the Earth is geologically alive. Volcanoes continued to erupt beneath the ice. They pumped carbon dioxide back into the atmosphere. Because the ice covered the rocks could not absorb the CO2. It built up. Slowly, the greenhouse effect returned. The heat built up. And then, the thaw began. The ice cracked. The oceans opened. Life emerged from the freeze into a new world, a world with an oxygen-rich atmosphere and a blue sky. The survivors of the oxygen crisis had adapted. They had learned a new trick, aerobic respiration. Instead of fearing oxygen, they learned to use it. They learned to burn their food with it. Using oxygen to burn sugar releases 18 times more energy than the old anaerobic methods. It was like switching from a candle to a jet engine. This surge in available energy allowed life to grow bigger. It allowed for complexity. And then another miracle occurred, the most important merger in history: endosymbiosis. Imagine a large, predatory single-celled organism. It swims through the ocean, eating smaller bacteria. One day, it engulfs a small, energy-efficient bacteria that knows how to use oxygen. Usually, the predator would digest the prey, but this time, something different happens. The small bacteria survives inside the large one. It strikes a deal. "I will make energy for you," it says, "if you protect me and give me food." The predator agrees. The two become one. The small internal bacteria evolves into the mitochondria, the powerhouse of the cell. Every cell in your body today is the descendant of this ancient merger. You are a colony of colonies. Later, some of these new complex cells swallowed a cyanobacterium, the photosynthesizer. This became the chloroplast. This lineage became the plants. This new type of cell, the eukaryote, was larger, more complex, and packed with energy. It had a nucleus to protect its DNA. It had internal factories. It was ready to build. For a long time, a period scientists call the Boring Billion, these eukaryotes lived quietly. They evolved sex, mixing their genes to create variation. They drifted in the oceans. But eventually, they learned to cooperate. Single cells began to stick together. They formed colonies. At first, every cell in the colony was the same, but then they began to specialize. "I will handle the movement," said the outer cells. "I will handle the digestion," said the inner cells. "I will handle the reproduction," said the germ cells. True multicellular life was born. The first animals appeared. They were simple, soft-bodied creatures: sponges, jellyfish, fronds that looked like ferns but lived in the dark depths, the Ediacaran biota. They had no eyes, no teeth, no hard shells. It was a Garden of Eden, a peaceful world of filter feeders drifting in the slow currents. But the peace would not last. The energy was too high. The potential for competition was too great. About 540 million years ago, the Cambrian explosion occurred. In a geological blink of an eye, all the major body plans of animals appeared. Eyes evolved. Suddenly, the predator could see the prey. Armor evolved. Hard shells, spikes, and claws. The arms race began. The ocean filled with trilobites, worms, and strange, alien creatures like Anomalocaris, a meter-long predator with grasping claws. The biological information explosion matched the Big Bang in its intensity. Life was diversifying into every niche, but the land was still barren. It was a world of rock and sand, perhaps covered in a thin slime of algae, but no trees, no grass, no animals. The continents were empty. The next great journey was the invasion of the land. The plants went first. Algae crept up the shorelines, adapting to the harsh, dry air. They evolved into mosses, then ferns. They developed waxy skins to hold in their water. They developed roots to mine the rock for minerals, turning stone into soil. They terraformed the continents. They pumped even more oxygen into the air. They created the ozone layer, a shield of gas that blocked the deadly ultraviolet radiation of the sun. Before ozone, the land was sterilized by the sun. Now it was safe. In the shadow of these first forests, the animals followed. Insects were likely the pioneers, scorpions and millipedes scurrying out of the water to eat the rotting vegetation. Because the oxygen levels were so high, they grew huge. Dragonflies with the wingspans of eagles, millipedes as long as cars. Then came the fish. A specific lineage of fish, the lobe-finned fish, lived in shallow, swampy waters. They had strong, fleshy fins that they used to push themselves through the mud. Over millions of years, these fins evolved into legs. The swim bladder, used for buoyancy, evolved into lungs. One day, a creature, perhaps Tiktaalik, pulled itself out of the water and onto the muddy bank. It looked around with eyes adapted for water, breathing air with difficulty. It was not staying. It probably went back in. But the threshold had been crossed. The amphibians had arrived. They were tethered to the water. They needed it to lay their eggs, but they could walk on the earth. They were followed by the reptiles, who developed a revolutionary technology, the amniotic egg, a waterproof shell that carried its own private ocean inside. With this egg, animals could leave the water behind completely. They could march into the deserts. They could conquer the interior of the continents. The age of reptiles began. The dinosaurs rose, dominating the planet for 150 million years. They were magnificent, diverse, and successful. They filled every niche, from the size of a chicken to the size of a building. But the universe is violent. We know how their story ended. A rock from the sky, a remnant of the solar system's chaotic birth, slammed into the Yucatan. The winter returned. The giants fell. But in the ashes of that catastrophe, a small, furry creature crawled out of its burrow, a mammal, our ancestor. The mammals had been living in the shadows of the dinosaurs for millions of years, staying small, nocturnal, and terrified. But with the tyrants gone, the world was open. They radiated outward. They grew large. They returned to the sea as whales. They took to the skies as bats. And one lineage took to the trees, the primates. They developed grasping hands to hold branches. They developed forward-facing eyes to judge distances for jumping. They developed large brains to navigate the complex social politics of the troop. And then the climate changed again. The forests of Africa dried up. The trees receded, leaving wide bands of open savanna grass. One ape was forced to come down from the trees. To see over the tall grass, it stood up on its hind legs. It became bipedal. This freed its hands. It could now carry things: food, tools, babies, fire. This brings us to the edge of the human story. But before we look at ourselves, we must pause and look at the planet itself. The Earth of today is unrecognizable from the Hadean hellscape we started with. It is a blue jewel, wrapped in white clouds, covered in green velvet. It is a living organism. The Gaia hypothesis suggests that life interacts with the inorganic surroundings to form a synergistic, self-regulating system. The plankton in the ocean produce clouds. The forests regulate the rainfall. The weathering of rocks regulates the temperature. Life does not just exist on the rock. Life is the rock. The limestone cliffs of Dover are made of the skeletons of trillions of microscopic creatures. The oil we burn is the compressed bodies of ancient algae. The oxygen we breathe is the exhalation of the biosphere. The Earth is a biological construct as much as a geological one. From the first second of the Big Bang, to the formation of the first atom, to the first star, to the first cell, to the first thought, it is an unbroken chain. Complexity has been increasing steadily, fighting the tide of entropy. The universe has been waking up, step by step. Matter learned to organize. Then it learned to replicate. Then it learned to sense. Then it learned to think. In the next chapter, we will explore the final leap, the leap from biology to consciousness. We will look at the human mind, the most complex object in the known universe. We will look at how a collection of neurons, made of the same atoms as the stars, can wake up and ask the question, where did I come from? We will see the birth of language, art, and science. We will see how the universe, through us, has finally developed the ability to tell its own story. For now, drift over the green earth. See the herds of animals migrating across the plains. See the whales breaching in the oceans. See the lights of the cities beginning to flick on as the sun sets. You are the product of 4 billion years of struggle, luck, and evolution. You are the leading edge of the wave. Rest in the knowledge that you belong here. You are the universe coming to know itself. We have watched the physical universe assemble itself, from the quark-gluon plasma to the spiral galaxy, from the dust grain to the blue planet. We have seen biology conquer the rock, wrapping the earth in a living skin. But for billions of years, this life was silent. It felt, it reacted, it survived. But it did not know that it existed. It was a play without an audience. Now, we reach the final and most mysterious threshold. We witness the moment when the lights turned on inside the house. We witness the birth of the observer. We return to the high grass of the African savanna, where a peculiar ape is about to change the destiny of the cosmos. The climate of Africa had dried. The lush, continuous canopy of the rainforests had shattered into islands of trees separated by vast oceans of grass. The apes that lived there faced a choice: retreat into the shrinking forests or venture out into the open. One lineage chose the open. To survive in the tall grass, they had to stand up. By standing on 2 legs, they could see the predators approaching. They could spot the water holes. But bipedalism did something even more profound. It freed the hands. For the first time, a creature could walk and carry. It could carry food. It could carry a baby. It could carry a weapon. The hand, no longer needed for locomotion, became an instrument of manipulation. It developed a precision grip, the opposable thumb pressing against the fingers, that allowed for delicate control. The hand became the first tool of the mind. With this hand, the ape picked up a stone. But it did not just throw the stone. It looked at it. It imagined a shape inside the stone that was not there. It struck the stone against another, chipping away the excess, revealing a sharp edge. This was the first act of engineering. It was the imposition of will upon matter. The stone hand axe was not just a rock. It was a fossilized thought. It proved that the creature could see the future. It could envision the tool it needed before the tool existed. But the true revolution began with a spark. Somewhere, sometime, a hominid conquered fire. Fire changed everything. Before fire, life was dictated by the sun. When the sun went down, the world was dark and dangerous. Predators ruled the night. But with fire, we pushed back the dark. We created our own day. We sat around the hearth, bathed in the warm, flickering light, safe from the lions. The campfire became the first school. It was the center of the tribe. In the circle of light, we looked at each other's faces. We bonded. We shared the events of the day. The fire forced us to be social. But fire did something even more critical. It cooked our food. Raw meat and tough roots are hard to digest. An ape spends 6 hours a day chewing. The energy cost of digestion is massive. But cooking pre-digests the food. It breaks down the proteins. It softens the fibers. It unlocks the calories. Suddenly, we had a surplus of energy. We didn't need huge guts to process raw leaves anymore. Our stomachs shrank, and the energy that was saved went to the most expensive organ in the body, the brain. The human brain is a furnace. It consumes 20% of the body's energy, despite being only 2% of its weight. Fire paid the bill for the brain. Cooking allowed us to grow a neocortex of unprecedented size. We ate our way to intelligence. As the brain grew, it began to do something new. It began to label the world. It invented language. Animals communicate. A vervet monkey has a specific cry for eagle and a different cry for snake. But this is not language. It is signaling. It is tied to the immediate moment. A monkey cannot say, "I saw a snake yesterday," or "I think there might be an eagle tomorrow." Human language broke the chains of the present. We developed syntax, the ability to arrange words in infinite combinations to describe things that are not happening right now. We could discuss the past. We could plan the future. We could describe things that do not exist at all. We could tell stories. We could create myths. We could say, "The river spirit wants us to move north." This allowed us to cooperate in groups larger than any other animal. A troop of chimpanzees falls apart if it gets larger than 50 members. They cannot keep track of the relationships. But humans, bound by shared stories and shared beliefs, could organize into tribes of hundreds, then thousands. Language turned the individual brain into a collective brain. If one person learned how to make a better spear, they could tell the tribe. The knowledge didn't die with the individual. It was passed down. It accumulated. Culture was born. With these tools, fire, stone, and language, we left Africa. We walked out into the unknown. We crossed the land bridges into Europe and Asia. We built boats and crossed to Australia. We walked across the ice of the Bering Strait into the Americas. We were the most invasive species the planet had ever seen. We adapted to every environment. We learned to wear the skins of other animals to survive the ice. We learned to read the stars to navigate the desert. We were not strong or fast or armored, but we were adaptable. But beneath the survival, a deeper change was happening. The I was emerging. Time threes. Go deep into a cave in France or Indonesia. Shine a light on the wall. You will see stencils of hands, red and ochre outlines, blown onto the rock 40,000 years ago. This is not survival. This is art. It is a declaration of existence. I was here. I am me. I am separate from the rock, separate from the tribe, separate from the world. This is the dawn of self-awareness. The universe had created a mirror. The atoms that were forged in the stars had rearranged themselves into a pattern that could look up at the stars and wonder. This awakening brought with it a terrible burden, the knowledge of death. Animals grieve, but they do not seem to ponder their own mortality. Humans do. We realized that our time was finite. We realized that the I would one day cease to be. We responded with ritual. We buried our dead. We placed flowers, beads, and tools in the graves. We imagined worlds beyond this one. We invented the afterlife to soothe the terror of non-existence. Religion was the first attempt to explain the universe, the first attempt to find order in the chaos. We looked at the sky and saw patterns. We connected the stars into constellations. We saw hunters, bears, and rivers in the dark. We projected our own stories onto the cosmos. For tens of thousands of years, we lived as hunter-gatherers. We were part of the ecosystem, just another predator, albeit a very smart one. But then the ice melted. The climate stabilized. About 10,000 years ago, in the Fertile Crescent, we made another choice. We stopped walking, we planted a seed, the agricultural revolution. We domesticated the wheat, and in turn, the wheat domesticated us. We cleared the forests to make fields. We built permanent houses. We built walls. Farming created a surplus of food. For the first time, not everyone had to hunt or gather. Some people could specialize. They could become potters, weavers, priests, kings. Cities rose. Jericho, Uruk, Mohenjo-Daro, vast hives of humanity. With the city came the need for records. Who owns this field? How much grain is in the silo? We pressed reeds into wet clay. Writing was born. Writing was the second great expansion of the mind. It allowed us to store memory outside the body. We could talk to the dead and speak to the unborn. Knowledge became durable. It could travel across time. Civilizations rose and fell, but the knowledge remained. Mathematics, astronomy, medicine, philosophy. We began to measure the world. We realized the Earth was a sphere. We calculated its size. We realized the Earth orbited the Sun. Then came the tools of vision. We ground glass into lenses. We put them in tubes. We looked down at the drop of water and saw the universe of the microbe. We looked up at the sky and saw the moons of Jupiter. We realized we were not the center of everything. We were small, living on a dust mote suspended in a sunbeam. This was the scientific revolution. It was a moment of humility, but also of power. We learned the language of the universe, mathematics. We discovered that the same force that drops the apple holds the moon. We discovered the laws of thermodynamics. We discovered electromagnetism. We learned to harness the energy of the earth. We dug up the coal, the fossilized sunlight of the carboniferous forests, and burned it to drive machines. The Industrial Revolution. We became the masters of energy. We learned to fly. We left the surface of the earth, first in balloons, then in planes. We looked down at our planet and saw it as a whole. And then we did the impossible. We broke the atom. We unlocked the strong nuclear force, the same force that powers the sun. We held the fire of the stars in our hands. We used it for war and then for power. We built rockets. We calculated the orbits. We put a human being on top of a pillar of fire and shot them into the void. Standing on the moon, looking back at the Earth rising over the lunar horizon, we completed a circle. The matter of the universe had evolved into a form that could leave its home and look back at itself. The universe had become self-aware. But what is this awareness? What is consciousness? This is the hard problem. We can explain the chemistry of the brain. We can trace the electrical signals. We can map the neurons. But we cannot explain the feeling, the redness of red, the ache of sorrow, the spark of joy. How does wet, gray biological tissue produce the sensation of being alive? We do not know. It is the greatest remaining mystery. Perhaps consciousness is a fundamental property of the universe, like gravity or charge, waiting to be tuned into by a complex enough system. Perhaps it is an emergent property, a ghost rising from the complexity of the machine. Whatever it is what makes the universe matter. Without a mind to perceive it, does the universe exist? Does the rainbow exist without an eye to see the colors? Does time exist without a memory to record it? We are the witnesses. we are the sense organs of the cosmos. Through our eyes, the universe sees its own beauty. Through our ears, it hears its own music. Through our minds, it understands its own laws. We have built a second layer of reality on top of the physical one, the noosphere, the sphere of thought. We have connected our minds with the internet, a global nervous system of light and glass. We are sharing our thoughts at the speed of light. We are becoming a planetary intelligence, but we are still fragile. We are still those apes on the savannah, driven by fear and tribalism, wielding the power of gods. We have the capacity to destroy the garden we have inherited. The story of the mind is not over. We are currently teaching sand to think. We are building artificial intelligence. We are creating a new kind of mind, one not born of biology, but of silicon and code. Will it be a partner, a successor, or a mirror? As we stand here at the peak of our technological power, we must remember where we came from. We are the result of a 14 billion year chain of accidents. The first second created the quarks. The stars created the carbon. The sun created the energy. The earth created the home. And the struggle for survival created the mind. We carry the history of the universe in our bodies. Our blood is the ocean. Our bones are the rocks. Our breath is the atmosphere. And our minds are the light. They are the part of the universe that has woken up. In the next and final chapter, we will look forward. We will look at the future of the universe. We have seen the beginning. Now we must see the end. We will explore the destiny of the Earth, the death of the sun, and the slow fading of the galaxies. We will look at the big freeze. But we will also look at the legacy of life. Can intelligence survive the death of its star? Can we spread to other worlds? Can the universe wake up completely? For now, simply be. Be aware of your own awareness. Notice the fact that you are noticing. That quiet observer behind your eyes, that is the most precious thing in existence. It is the flame that the universe spent 14 billion years trying to light. Guard it well. Rest in the wonder of your own being. We have traveled a distance that defies imagination. We began at the Planck Epoch, a moment of infinite heat and density, smaller than an atom. We watched the universe inflate, cool, and forge the first elements. We saw the lights turn on, the galaxies spin, and the Earth coalesce from the dust. We watched life crawl from the vents to the land, and finally wake up to look at the stars. Now we stand at the peak of the story. We are living in the stelliferous era, the era of stars. It is the brief, beautiful summer of the universe. But like all summers, it must eventually turn to autumn. The arrow of time that was fired in the first second is still flying, and it points toward a distant, silent future. To understand the full story, we must look forward. We must witness the long, slow fading of the light. Our journey into the deep future begins close to home. It begins with the object that gave us life, the sun. For 4.5 billion years, the sun has been a faithful guardian, burning hydrogen in a steady, stable rhythm. But stars are not static machines. They evolve. They change. As the sun burns, it accumulates helium ash in its core. This ash makes the core denser and hotter. Paradoxically, as the star runs out of fuel, it burns brighter. In about 1 billion years, the sun will be 10% more luminous than it is today. This sounds like a small change, but for the delicate balance of the Earth, it is catastrophic. The extra heat will begin to evaporate the oceans. The atmosphere will fill with water vapor, which is a potent greenhouse gas. A runaway effect will trigger. The Earth will become a sweltering, steam-filled hothouse, much like Venus is today. Complex life, the forests, the whales, the cities, will not survive this shift. The biosphere will retreat back into the microbial world, hiding in the last deep pockets of water or underground caves. But the sun is not done. In about 5 billion years, the hydrogen in the core will be exhausted. The hydrostatic balance, the war between gravity and light, will break. The core will collapse, and the outer layers of the star will swell outward. The sun will become a red giant. It will grow terrifyingly large. It will swallow the orbit of Mercury. It will swallow the orbit of Venus. It will loom in the sky of Earth, a wall of angry red fire spanning from horizon to horizon. The rock of our planet will melt. The atmosphere will be stripped away. The cradle of humanity will be sterilized by its creator. And then the end comes. The sun will shed its outer layers, puffing them gently into space to form a planetary nebula, a beautiful, glowing flower of gas. The core will remain behind as a white dwarf, a tiny, dense crystal of carbon and oxygen, glowing with the last trapped heat of its youth. It will be the size of the Earth, but with the mass of a star, a diamond in the dark. While our solar system is dying, a greater drama is playing out on the galactic stage. Look up at the constellation Andromeda. There is a smudge of light there. That is the Andromeda Galaxy, a city of 1 trillion stars, and it is rushing toward us. Gravity is pulling the Milky Way and Andromeda together at a speed of 110 kilometers per second. In about 4 billion years, just as our sun is swelling, the two galaxies will meet. It will not be a crash, but a merger, a ghostly passing through. The spaces between stars are so vast that individual stars will almost never collide, but the gas clouds, the nebulas, will smash together. This will trigger a furious burst of new star formation. The night sky will be ablaze with the blue light of newborn giants. The spiral arms of both galaxies will be torn apart, flung out into long tidal tails of light. Over hundreds of millions of years, the two structures will settle down. They will merge into a single, giant, elliptical galaxy. Astronomers have named this future home Milkdromeda. For a while, Milkdromeda will be bright and active, but the universe is running on a limited budget. There is only so much hydrogen gas available. Every time a star forms, it locks away some of that gas. When it dies, it returns some gas to the galaxy, but not all of it. Much of it is trapped in white dwarfs, neutron stars, and black holes. Slowly, the gas reserves of the universe are being depleted. The rate of star formation will drop. The brilliant blue stars, the ones that live fast and die young, will vanish first, exploding as supernovae and fading into memory. The universe will change color. As the blue stars disappear, only the yellow and red stars will remain. The galaxies will dim and redden. We are moving from the vibrant summer of the cosmos into the long, golden autumn. Eventually, the last gas cloud will collapse. The last new star will be born. We do not know when this will happen, perhaps in 100 trillion years. But the moment will come. The universe will cease to be a nursery. It will become a retirement home. The only stars left will be the red dwarfs. These tiny, frugal stars burn their fuel so slowly that they can live for trillions of years. They will be the last lanterns in the dark. civilizations of the deep future will huddle around them, gathering the meager warmth, remembering the days when the sky was filled with giants. But even the red dwarfs are mortal. One by one, they will exhaust their fuel. They will not explode. They will simply fade. They will shrink into white dwarfs and then cool down over eons to become black dwarfs, cold, dark balls of degenerate matter, floating, invisible in the void. When the last red dwarf goes dark, the stelliferous era will end. The age of starlight will be over. The universe will be black. We will enter the degenerate era. The cosmos will be a graveyard of stellar remnants. White dwarfs, neutron stars, and black holes will drift through the expanding darkness. Occasionally, two of them might collide, creating a brief flash of light, a supernova in the dark. But these will be rare flickers in an endless night. In this era, gravity will continue its work. The dead stars will interact. Through dynamical friction, they will trade energy. Some will be flung out of the galaxy into the intergalactic void, destined to drift alone forever. Others will lose energy and sink toward the center. At the center of the galaxy, the supermassive black hole waits. It has grown fat over the eons, consuming gas and stars. Now, it will consume the remnants. The white dwarfs and neutron stars that sink to the center will be swallowed. But even matter itself may not be eternal. Many physicists believe that the proton, the building block of the atomic nucleus, is not stable. They hypothesize that over timescales of 10 to the power of 30 years, protons will decay. If this is true, then the dead stars, the white dwarfs and neutron stars, will not last forever. They will slowly dissolve. The matter that makes them up will break down into lighter particles and radiation. The solid objects of the universe will simply melt away into light. This leaves only one thing: the black holes. We enter the black hole era. For a length of time that defies human comprehension, the universe will contain nothing but black holes and waste radiation. These monsters will drift through a space that has expanded to unimaginable vastness. The distance between them will be so great that they will never interact. Each one will be a solitary king of a dead domain. But as we learned in the story of black holes, even they are not immortal. Stephen Hawking showed us that they leak. Through quantum processes at the event horizon, they emit Hawking radiation. They glow. They lose mass very, very slowly. It takes a Google years, a 1 followed by 100 zeros, for the supermassive black holes to evaporate. But time is the one thing the universe has in abundance. As they shrink, they get hotter. In their final moments, they will explode with the force of 1 billion nuclear bombs, releasing their trapped energy back into the universe as a burst of gamma rays. One by one, across the dark expanse, the black holes will pop and vanish. The last structures of the universe will be erased. And then we reach the end, the dark era, the heat death. The universe is now a sea of photons, neutrinos, and electrons, spread out over distances so vast that they rarely, if ever, meet. The temperature drops to absolute zero. The expansion of space continues, stretching the light until it has almost no energy left. Entropy has reached its maximum. The deck of cards has been shuffled so thoroughly that no order remains. The arrow of time loses its meaning, for nothing changes. There is no before or after, when the state of the universe is the same forever. This sounds like a tragedy, a cold, lonely ending to the magnificent firework display that was the Big Bang. But there is another way to look at it. The heat, death, is a state of perfect equilibrium. It is a state of rest. The tension that began in the first second, the separation of forces, the clumping of matter has finally been resolved. The universe has exhaled. And perhaps it is not the end. Some physicists speculate that in this state of pure vacuum energy, quantum fluctuations could trigger a new Big Bang, a little bang in the void. Or perhaps our universe is just one bubble in a frothing multiverse, and while ours dies, others are being born. But let us return from the abyss. Let us zoom back from the Google years to the present day, to the year you are living in. Look at where we stand in this timeline. We are not at the beginning, and we are certainly not at the end. We are in the Goldilocks zone of time. The universe is cool enough for atoms to exist, but warm enough for stars to burn. It is old enough for carbon and oxygen to have built up, but young enough that the fuel hasn't run out. It is the only time in the history of the cosmos when life is possible. We are living in the Golden Age. We are the witnesses that the universe produced to watch its own glory. Think of the improbability of your existence. The first second had to happen exactly as it did. If the expansion had been slightly faster, matter would have flown apart too quickly to form stars. If it had been slightly slower, the universe would have collapsed back into a black hole. If the ratio of matter to antimatter had been equal, there would be nothing but light. If the carbon atom didn't have a specific resonance, stars couldn't forge the building blocks of life. Rate 100%. Pitch 1%. You are the winner of a lottery that has been running for 14 billion years. The atoms in your hand have traveled through supernovas and nebulas, through the accretion disk of the sun, through the molten rocks of the early Earth, through the biology of dinosaurs and ancestors, to be here, right now, holding this device, listening to this story. This gives us a responsibility. We are the custodians of meaning. The universe itself does not care. Gravity does not care. Entropy does not care. But we care. We create beauty. We create love. We create knowledge. We are the way the universe feels emotions. As far as we know, we are the only ones. We have scanned the skies for radio signals and heard only silence. We might be the only island of consciousness in the entire dark sea. This makes every moment precious. Every breath you take is a victory against the void. Every thought you have is a defiance of entropy. So, as you lie in bed tonight, do not worry about the heat death. That is a story for the atoms, trillions of years from now. Worrying about it is like a single wave worrying about the evaporation of the ocean. Instead, feel the gravity holding you. It is the same gravity that held the first stars together. Feel the warmth of your blankets. It is the same energy that was born in the Big Bang, changed form 1,000 times, and is now keeping you warm. Look at the darkness behind your eyelids. It is not empty. It is the canvas upon which your mind paints. You are a child of the first second. You are the legacy of the stars. You are the universe, awake and dreaming. The story of the universe is not once upon a time. The story is happening now. You are the story. Rest in that greatness. Let the expansion carry you into sleep. The stars are watching over you, just as they watched over the first life on Earth. May your sleep be deep, your dreams be vast, and your waking be filled with the wonder of existing. Good night.